All right. So thank you all for attending. Once again, we have Dr. Cezar Lupu from Texas Tech, who is thankfully wearing a Pitt shirt, right? So he was a grad student at Pitt, as most of you know,
And also look at my background too.
also the cathedral, right? And he's going to give a talk on the Basel problem and some more zeta function things. So Cezar, whenever you want to share your screen, go for it.
All right, thank you very much. Okay, let me do it now. So just like Derek said, I will talk about the Basel problem, but in fact, I will I will show another solution to this Basel problem. And it's more, the approach is more suitable for in fact, I would say even for an advanced calc student, definitely. So you will see a bunch of integrals, mean value theorems. But before I dive and show you those two proofs, and in fact, we can, I will show you even more than that, more than just the Basel problem using the similar ideas. I'd like to say a few things about the Basel problem. So let me start with the Basel problem, with some history about it. Because in fact, I looked, I always, I didn't know the whole history about the Basel problem. I knew a bunch of things, but not the whole history. And it looks like it was a conjecture for almost 100 years. I didn't even know that. So the Basel problem states the following. So it was that in 1734, so this is how, well, I'm not going to start chronologically talking about this, but in 1734, Leonhard Euler, so probably you've heard of this guy, proved the following proved the following result. And, well, I would say striking result, which is the following. This series, the sum from n equals 1 to infinity of 1 over n squared is nothing else than just pi squared over 6. And surprisingly, the proof given by Euler is 1734, but it will officially it was announced in 1735. So this guy here, it's okay. Let's just say that this is 1.644934. All right. So, like I said, this problem has relevance to analysis. And here, when I say analysis, I mean complex, real analysis, whatever, and number theory. In number theory, it's extremely important. This gave birth to the study of L functions or modular forms or automorphic forms and so on. But at the beginning, this was conjectured. So it was first conjectured. So it was first conjectured by this mathematician, Pietro Mangoli. I'm not sure, I hope I'm not mistaken. I think it was Euler's advisor, but anyway, maybe not. Anyway, so Pietro Mangoli, this was conjectured around 1650. So he conjectured this for the first time to find out the sum of this series. Well, like I said, Euler proved it in 1734, but in fact his first proof was well, wrong, but the result was correct. In fact, Euler was ahead of his time, so he was already doing formal series without even knowing what they were. But officially it was announced, Euler announced the result on December 5th, 1 year later, 1735. So he announced it in the St. Petersburg Academy of Sciences. So at that time, he lived in Russia. Anyway, so this is a little bit of the history of this problem. Moreover, in fact, after he found this result, he was tempted to find other values as well. So we can say that Euler, the same Euler, studied what we call today the famous Riemann zeta function, the values of the Riemann zeta function, but for real argument. And when I say real argument, I mean about this. So zeta of x is the sum, is this series of 1 over n to the power x, and this x is a real number which is greater than 1. Well, probably you have seen this, and I mean, you can, in fact, this is taught even in Calc 2, I believe, when you discuss about the convergence of series, and you know the harmonic series, and you know that this converges when x is greater than 1. Well, so he's just like I said, Euler studied the values of this. So when I say the values, I mean other values such as zeta of 3, zeta of 4, zeta of 5, and so on, zeta of 6, and so on. Well, with some of them he had success, with some others he didn't, especially with the odd zeta values. But in fact, later on he even found a formula for zeta of 4, zeta of 6, and for all even values of the zeta function. And now, since we introduced this function, the Riemann zeta function, well, like I said, we can call this Euler Riemann function if you want. We can say that this is nothing else the value for a 2. So this will be nothing else than just zeta of 2 equals this series. So today we'll be focusing especially on this. Probably you have seen, or those of you who were interested in this problem have seen numerous proofs for this. Well, some of them, usually the standard proof that is given these days, it appears in a functional analysis course or a Fourier series course, where they just apply you just take the Fourier series of the x squared function, and then you find immediately the value of zeta of 2. But anyway, suppose we don't have, back in those days, Euler didn't have all this machinery. And let me just say a few words of how Euler proved it, because I said, so the first question, how did Euler prove it? So how did he prove this? Well, there are a bunch of ingredients here, right? And I would like to talk about these ingredients. Well, the first thing that he did is to, so first thing, consider the following Maclaurin expansion. Expansion of sign, but I'm going to consider it in this way. Even from calculus 1 or 2, this can be expanded in the following. So it's pi x minus pi x cubed over 3 factorial plus pi x to the 5th over 5 factorial. And we keep going. In other words, this is nothing else, if we want to write it as a series, this is nothing else than just -1 to the power m plus 1 times p pi to the power m plus 1 over 2m plus 1 factorial. And here I can squeeze times x to the power m plus 1. Okay, so this is the power series, the Maclaurin expansion for, and of course this goes from n equals 1 to infinity, of sine of x. And what Euler did, and this is why it's wrong, he denoted this like a polynomial. Let's just say this is a p of x. So he was looking for the roots of this polynomial. So we know that the roots of p of x, the roots of p of x are integers, right? You know how they look like. They're k pi, something like this. And now what he did is the following. So he also expanded this polynomial in a product. So we also we can also write this polynomial p of x in the following way. So we can factor here pi x, and this will be 1 minus x over 1 times x plus, 1 plus x over 1, and we keep going, and x over 2 times x plus 2, and so on. In other words, this will be nothing else. If you want to write this will be pi x times 1 minus 1 minus x squared over 1 times 1 minus x squared over 2, and so on. Or you can write this as pi x. This is the Euler's, what we call these days Euler's infinite product for the sine, which looks like this. Anyway, what he did is the following. So we examine the coefficient of, so examine the coefficient of x cubed in both expansions. And once we do this, you'll see that, well, I'm missing some details here. And we have the following. So once we do this, in both the product formula and in the Maclaurin expansion, if you look at you look at the coefficient of x cubed here is what is so you'll get that so you'll get that negative pi cubed over 3 factorial is something like negative pi when you examine 1 over 1 plus 1 over 4 plus 1 over 9 and so on, right? Which is nothing else than negative pi times this. And you get the result. So this is how Euler proved it. Well, he assumed some things about finite polynomials to work in the infinite case, which was not quite true. But anyway, he came up with the whole theory of developing this infinite product formula. And we know these days that this holds even much more generally for other like hypergeometric functions and so on. Anyway, I'm not going to get into the proof of this. But this is the, roughly speaking, this is what Euler did. But now I would like to, so this is the Basel problem. I would like to go and talk a bit about something else, about the mean value, something which I don't know, for some reason is overlooked in a calculus 1 or 2 courses, but I think it's more, I think it's done in more details in advanced course or introduction to analysis course. And I would like to say a few words about mean value theorems for integrals. I see a bunch of people here like, all right. So mean value theorems for integrals. And what I would like to say, the first, I would like to, well, I will classify them in the following way. So the first mean value theorem for integrals, right? Okay, it's you can understand it's for integrals. The first mean value theorem, and I'll write it in the following way. So if I have a function, so which is defined on a closed and bounded interval AB, which is continuous, then we have the following. Okay, let me write it in this way. That the integral from a to b of f of x dx is b minus a, right? This is b minus a times f of c for some c in AB, right? If you look at this, this is nothing else than just a classical mean value theorem for the antiderivative. And if you look at this, well, if you divide by b minus a, this is nothing else than the average value of f, right? And this is the first mean value theorem. I think it's done in even in a Calculus 1 course. But now the second one, which is second mean value theorem, states the following. So again, this time I will have two functions. So I will have f and g defined from the same interval, closed and bounded interval AB. And these functions are continuous. And moreover, so continuous on AB. And moreover, we know that G has a property, and let's just say G has a constant sign. So G of x is not zero for all x in AB. Then we have the following. Okay, I'm going to squeeze this in here. So we can write this, this integral, the integral of the product of the two functions, as f of c times the integral from a to b of g of x dx for some c in AB. All right, so this is the second mean value theorem. In fact, I even put these two problems as an exam problem at my advanced calc course that I taught here at Tech. Well, it was in a different context, but anyway, you can actually derive this from Rolle's theorem immediately, both of them. And moreover, there is another one, which we will call the third mean value theorem. Right? The third mean value theorem, well, or sometimes it's called Bonnet-Weierstrass. Which is not quite well known. This does not appear in any, unfortunately, any calculus textbook or whatever, which says the following. So again, I'll have two functions, let's say f and g, defined on AB. Let's say f is continuous. Well, in fact, you can say it's just integrable, but anyway, let's just say it's continuous, and g is increasing on the interval AB. So both of them. Then guess what happens? Well, we'll have the following formula. then we will have that, again, the integral of the product is nothing else than just g evaluated at a times the integral from a to some c of f of x plus g evaluated at b times the integral from c to b of f of x dx, sorry. For some c in AB. Okay, so this is the third mean value theorem. Probably some of you, well, I haven't seen this before, but it's, well, it's not that popular, unfortunately. It's, well, there aren't too many applications of it, but I will show you one. Well,
Cezar,
yes.
could I say something?
Yes, please.
So so does G can G also be just like non-decreasing? Because I feel like constants could also work for this.
Yes, yes. Maybe I should say, well, I mean increasing, not strictly increasing. Okay, let me just put here non-decreasing. I think that's.
Or and to kind of build off that, so the thing says like this integral of this product is equal to this for some C in AB.
Yes.
So it doesn't say for all C in AB, but if
No.
G so if G was a constant function, it would be for all. So maybe that's why that they're saying increasing, because they don't want all C, they just want one C.
Yeah, exactly. Anyway.
That could be why.
Anyway, yeah, exactly. But anyway, just like I said, this is not done in any, I haven't seen it in any calculus textbook. And if you Google about Bonnet-Weierstrass theorem, mean value theorem, you're going to find some papers back in the day, in the early 1900s, about to prove this theorem. It looks like Bonnet and Weierstrass's proof was a little bit, well, I won't say complicated, but some people wanted to find easier proofs. Well, that's a tendency usually in math. All right, so I would like you to look at these two theorems. Sometimes people, well, I classify them in this way, but sometimes people want to say that the second mean value theorem is actually the first mean value theorem. So they don't want to say that, so they just want to say that the second mean value theorem is in fact the first mean value theorem, and the third mean value theorem is nothing else than just the second mean value theorem, or Bonnet-Weierstrass mean value theorem. But anyway, I classify them in this way, and I would like to make one small comment. As you can see, the first mean value theorem follows immediately from the second mean value theorem. I think that's obvious. You just have to take G to be constant function 1, and then there you go. All right, so now the question is, what is the connection between, well, so let's address this question. How are the second, okay, let me write it in this way, and the third mean value theorems or for integrals? I want to be, anyway, this is redundant, but I want to mention it. So how are these related to values of, okay, to the Basel problem? You will see that they're quite related, but there is from us to go from these mean value theorems to the Basel problem, we need one other ingredient. And the short answer I'm going to give you, and in fact this will be a little bit vague, is what we call, well, the short answer is what we call the Dirichlet kernel. And I will say a few words about this, because this is very important when you study Fourier series. you'll see when you talk about the convergence of the Fourier series, you have to talk about the Dirichlet kernel. So, so this is related. To Fourier series. There is no way you can avoid talking about Fourier series without talking about the Dirichlet kernel. Okay, and now I would like to say a few words so that you can see well, to give you just a bit of an insight to what the Dirichlet kernel is all about. So roughly speaking, when we talk about the convergence, just like I said, when we talk about the convergence of the Fourier series, we deal with this Dirichlet kernel. And now, let me just say a few things. Suppose that, so what are these Fourier series all about? Let me say a few words. Yeah. Oh, suppose that f of x is a periodic function. Let's say with period 2 pi. Well, when you have a periodic function of period 2 pi, Fourier came with this amazing discovery. Oops. We know that that the Fourier series of f, that the Fourier series of f of x is given by the following expression. So I'm going to write it in this form. So it's going to be a0 plus the sum of an cosine of nx plus bn times sine of nx. So this is how we can write a function, the Fourier series of a function. And where this coefficients can be determined, where a0 is given by this guy, the 1 over 2 pi times the integral from negative pi pi of f of x dx, and this guy an is 1 over pi the integral of f of x times cosine of nx dx, and as you can imagine, bn is 1 over pi times the, so these are the Fourier coefficients, let's say, sine of nx. And guess what? When you look at this Fourier series, right? Look at this guy. So this is the Fourier series of my function f. And when you substitute the values of these coefficients into the partial sum, right? You can consider the partial sum. So the partial sum of the Fourier series is given by, well, let's just call this Sn from partial sum, is nothing else than just a0 plus, let's just write it in this way. So the sum from k equals 1, sorry, to n of ak cosine of kx plus bk cosine of kx. All right, so when we substitute all these coefficients here, we get the following, and hold your breath a bit because you'll get the following result for the partial sum. So Sn of x will be nothing else than just the integral. So we'll get this convoluted integral. So we'll write this in the following way: dn of x minus y f of y dy. So this is what we're getting. Anyway, I just changed a bit the variables here. It doesn't really matter that much, but imagine that this is the convolution between dn of my function f, where this guy dn of x, let's just write it, this is what we will call the Dirichlet kernel. This is nothing else than just, okay, I'm going to write it in this way: 1 over 2 pi times 1 plus 2, the sum of, from k equals 1 to n, of cosine of kx. So this is the Dirichlet kernel. As you can see, it's a function. It's a very nice function. And moreover, if you want to use like elementary trigonometric identities, you can write this in. So moreover, one can write this Dirichlet kernel as, again, this is an important formula, so we can write this in the following way. So it's a sine of m plus 1/2 x times x over 2 sine. Sometimes people put 2 pi. Okay, it doesn't really matter. It's okay. I'm going to put 2 pi here. Sine of x over 2. It doesn't really matter that much. Some people put pi here. Some people don't. But anyway, this is how we this is well, just a little bit about a glimpse of what the Dirichlet kernel is all about. But for example, the passing from here to here, there is one identity that is hidden, and this will be an important ingredient for us when we deal with the Basel problem. So the identity that is, in fact, let me write this expression. So this is 1, and this is 2, and the hidden identity here, well, it's not that hidden, but anyway, is the following. So I'm going to write it. So it's 1/2 plus the sum of all these cosines, right? Is nothing else than just the sine of m plus 1, sine of m plus 1/2 x over 2 sine of x squared. That's why I was saying that some people don't like to put that pi over there. So anyway, let's keep this identity in mind. I'm going to denote this by HI, let's say, hidden identity. And guess what? This will be one of the ingredients that we will use for our computation of zeta of 2. All right, and now we can, yes, I do have enough time. So I would like to talk about the main purpose of today's talk. So the proofs of Stark and Moreno for the Basel problem. Right. Okay. So now I'm gonna tell you about these 2 papers published in the American Mathematical Monthly. Well, one of them, I think it was in the monthly, the other one was in College Mathematics Journal. So both these journals are accessible, I hope, to any undergraduate student. And let me start with Stark's proof. This was, I think, given back in 1978. It's like a 2 pages note in the monthly. And let me, before I even start and tell you about the actual diving into the actual proof, let me tell you about the main ingredients. So that you can have an idea of what he used. So the main ingredients of the proof is the following: is the third mean value theorem. So like I said, Bonnet-Weierstrass theorem. Right? And the other ingredient that was well, I would say the Dirichlet kernel, but more, okay, let me write it this way, Dirichlet kernel. But I would like to say that it's more exactly is this hidden identity that you see here. Right? So this is these are the main ingredients for the proof of this. Okay, so now let's just say a few words about the actual proof. The proof will be quite short. The main idea is the following. So we need to come up with a certain integral. So that's I would say the ingenuity for this proof. So we're going to set the following. M sub n will be this integral from 0 to pi of, I'm going to take, let's say, t, and I'm going to multiply this by the Dirichlet kernel. So I want to consider this integral. And now, here where the identity will come into play. You see, I can, both of this are, let's say, the Dirichlet kernel, right? But you see, I can write it in two ways. I can write this in as 1/2 plus that sum, that finite sum of cosine, or I can also look at that quotient of the sines, right? Well, okay, let me say it explicitly. dn of t, I'll write it in this way, so it's 1/2 plus the sum of the cosine, right? But also this guy is the sine of all right. Okay, so we have this, and this is for all right. So this is the Dirichlet kernel. And now what we're going to do is the following. So we're going to take this expression, that's the trick here. I'm going to take this one here, I'm going to plug it in here, and to see what's going on. And then on the other hand, I'm going to take this other one here. In fact, maybe I shouldn't use this color. I will take this other one here, I'll plug it in here, and I'll get some other expression. But you know, with this function, with this ratio here, maybe it's a little bit harder to handle when we try to integrate, so I don't want to do that. So this is where the third mean value will come into play, so we can get rid of this. But on the first, if you look at that finite sum of cosines, this can be integrated. So we can say that partial integration will give us well, let's just say will give us the following. So it will be m sub 2m minus 1. So I'm going to write it in this one. You'll see immediately why. This is pi squared minus 8. And this will be the sum from k equals 1 to m of 1 over 2k minus 1 squared. Right? Anyway, I'll leave this to you, the details to you. It's just the integration of if you plug it in. You'll see the first part, you can get it immediately, and then you'll see that you will have a 2 factor there. You can, all right. Okay, but on the other hand, so here I use this finite sum with the cosine. And now on the other hand, what do we have? We will use the second expression for the Dirichlet kernel. So we will have that m sub 2m minus 1. This guy will be the integral from 0 to pi of, and now I'm just going to plug in, right? So this will be, so I know it's t, so it's t over sine of t over 2, right? Okay, I'm going to write it in this way, times sine of, and now if I plug in 2m minus 1, so this will be 4m minus 1 2 dt. All right, so I wrote it in this way because now we're in a good position to apply the third mean value theorem. And what I'm going to do is to apply the third mean value theorem right? The Bonnet-Weierstrass theorem. And for the following functions, for f of x, so I'm going to take f of x to be sine of 4m minus 1 of x, okay, x over 2. Right? And of course, this is a continuous function on 0 pi, so I don't have any problems. And my function g of x will be nothing else than just x over 2, everything over sine of x over 2, right? There's this function right here. So if you look at it, so this is my g, and this is my f. Well, you can show that this is an increasing function. I'll leave this to you. Okay, and moreover, we want to look at the boundary of g, and g of 0 is 1, and g of pi is pi over 2. And now we can get going. So we'll have the following. So it follows that m to m minus 1, which is nothing else than the integral from 0 to pi of this guy. Okay, let me write it again. T over sine of t over 2 times sine of 4m minus 1 t over 2. So this guy here, right? This guy will be equal to 1 times the integral from 0 to c of sine of 4m minus 1 t over 2 dt plus pi over 2 times the integral from c to pi of sine of 4m minus 1 t over 2 dt, which will give us, after we putting everything together, this will be, okay, I'm just gonna write it, so this will be something like this, pi over 2 minus 1 cosine of 4m minus 1 c over 2, right, times 1 over 4m minus 1. Well, this clearly is some kind of a O of 1 over m as m approaches infinity. So we don't have any problems. This will go to 0. And now guess what? Look at this expression here. It will follow immediately that this guy goes to 0. So as n approaches infinity, we have that, well, we can say that this series, in fact, of 1 over 2n minus 1 squared is pi squared over 8. But from here, I'll leave this to you. It will follow immediately that this sum is 1 over n squared pi squared over 6. All right, so that's the first proof. Derek, how much time do I have?
You probably have maybe, 7, 9
Okay.
minutes or something.
All right.
I mean, if you go over, it's okay.
Okay, I'll go a bit over. So this is the proof of Stark. To be honest with you, I would like to, the second proof that I will present, it's nicer, it's shorter. So Moreno's proof, in fact, this will be immediate. And this was published in 2016. Again, this will be simpler because I don't need the third mean value theorem. So the main ingredients here are the second mean value theorem, and again, the Dirichlet kernel, the same identity. In fact, that hidden identity, I'm going to use it again. But you will see that the proof now will be much, much shorter. So again, I'm going to start with the same identity. So again, we start with Now you'll see that I will tweak this a bit. So we start with the identity, with the hidden identity again. Let me just write it, copy it so that I have it here, so that you can see it better. So this will be k cosine of kx. So this will be sine of n plus 1/2 times x over 2 sine of x over 2. All right. So I'm going to start with this identity again. But now what I'm going to do, I'm going to multiply by a polynomial. So I'm going to multiply this, this identity, so let's say hi, by the following, let's say, quadratic polynomial. In fact, this is a phenomena hidden here. And let me say write the polynomial in the following way. It's x squared minus 2 pi x. And maybe you'll wonder where this polynomial comes from. Well, and we integrate over the interval 0 pi. So once we have this, we have the following. So we will, okay, I'm just gonna tell you what we get. So we'll get something like negative pi, let me see. Okay, so it'll be pi cubed plus 3 plus, and here I'll get this sum. So I'm gonna write it in this way, 2 pi over k squared, right? As you can see here, I have this term. And this will be the integral from 0 to pi of x minus 2 pi times x over 2 over sine of x over 2, right? Let's be careful here, times sine of n plus 1/2 x, okay, dx. All right, what we're going to do is the following. I'm just going to explain the procedure. So this guy, let's imagine that this guy is a function, is a u, and this guy here is a dv. So as you can expect, I will integrate by parts. So integration by parts will give us the following. Well, it will give us something like this. So it will be uv, so it will be x minus 2 pi times x over 2 over sine of x over 2, right? Times uv, which will be, well, you can imagine what function. So we have, what do we have? It's cosine of n plus 1/2 x over n plus 1/2. And we have, wait, what? So it's negative here, sorry. Yeah, it's n plus 1/2, okay. So that's u and v. So this is u, this is v. And now from 0 to pi, let's not forget that, minus, and here I'll have minus the integral from 0 to pi of negative cosine of n plus 1/2 x over n plus 1/2, right? Times, and I'm not going to write the function. I don't want to compute the derivative of this, and you will see why. Du dx dx. Okay, right? So this guy is du. This guy is v. So that's the integration by parts. And now, well, if we see you have negative here, it will become positive. But I'm just going to write directly since I don't want to lose too much time. Well, I went a bit over time, if I look. So this will be nothing else than just, now using, here I'm going to use the second mean value theorem, right? And this will give us something like, you see, I'm going to use this second mean value theorem for this integral. I'm going to, here, right? So I'm going to take out this v. So this would be negative 2 pi over n plus 1/2 plus, and here I'll have cosine of n plus 1/2, and here I'll have a number Cn, which depends on n, everything over n plus 1/2, right? Times the integral from 0 to pi of du dx dx. And for this guy here, as you can imagine, for this guy here, I can apply the fundamental theorem of calculus. And guess what? This will give me, well, at some point, I think I've done some computations here. Let me find them, because I don't want to, okay. So at some point, we will have something, okay, I'm going to leave, at some point, I will get something like this, negative 2 pi plus 2 pi minus pi squared over 2 times cosine of n plus 1/2 times Cn. And this will be everything over n plus 1/2. And as you can imagine, as n approaches infinity, this will approach 0. Well, where did we start from? So we start from here. Look at this guy. At one hand is this guy. On the other hand, it goes to 0. So it follows that. So finally, it follows that the limit as n approaches infinity, so of that guy, which is this guy here, negative pi over 3, negative pi squared over 3 plus the sum from k equals of 2 pi over k squared is 0. And you will get the result, and the conclusion follows. We'll get immediately the Basel problem. Okay, so that's the end of the proof. And well, I would have wanted to say, to give you a bit more of an insight of how to compute zeta of 4 and zeta of 6 even. But anyway, I'll stop here. Thank you very much.
All right. Let's all thank Cezar. So, thank you. This was a really good talk. I think even some of it kind of has like talks kind of like within each other, you know, like to get through all the formalities and stuff.
Yeah.
But it shows nice nice behaviors of functions and really just like integration by parts, you know.
Yeah, exactly. Basically, it's just integration by parts. Well, you have to choose those functions in a smart way.
Right.
And anyway, if you think of Dirichlet kernel, then yes, you can get many things. I mean, it's very useful in Fourier analysis.
So so does anyone have any questions for Cezar? Well, I do have a question actually.
Yeah, okay.
So essentially both proofs. So like one was doing x times the Dirichlet kernel.
Yes.
And then this one here was just doing a different function times the
Yes.
the Dirichlet, like 2 pi x minus x squared or something. I don't know.
Yes. In fact, if you
yeah x squared minus 2 pi x. So both of them kind of had the same concept of multiplying a function by this Dirichlet kernel.
Yes, exactly.
So I was thinking in the first proof when you do x times the Dirichlet kernel and you get your zeta 2s, maybe multiplying by x squared times the Dirichlet kernel would do something with zeta 3s, but I'm assuming that's not the case.
Frankly, I haven't tried it. For me, the Stark's proof, well, the first proof, it's more like everything just fits into the picture perfectly, but I don't see any ways to explore this further. So I like more the second proof because, well, I didn't have time, but you see, when you look at this polynomial here, x squared minus 2 pi x, surprisingly, this is related to Bernoulli's polynomial. So if you look at Bernoulli's polynomials for quadratic and so on, you will see that in this way, well, I didn't Well, I didn't use the Moreno's approach. I modified the Moreno's approach. Maybe I'll use a different identity. Maybe I'll have something with sign. And then another smart choice of polynomials, well, which are related to Bernoulli polynomials, will give you a proof for zeta, well, for zeta of 2 in the first instance, and then for zeta of 4, 6, and so on. And surprisingly, it gives you a proof even for zeta of 2n, for all values, the even values.
So the like x squared minus 2 pi x can be expanded to be a general polynomial
Yes.
that works for any odd power or for any even power.
Yes, something like this, yeah. But you have to modify it in a different way. Frankly, I don't know how to continue Moreno's approach to finding zeta of 4 and zeta of 6. But if you modify this approach and use another type of identity, just not the one with the Dirichlet kernel, but something different, maybe with Fourier kernel, you'll get even something, you'll get zeta of 2n. In fact, I do have a proof for this. Maybe I'll present it in a different seminar, maybe, I don't know, algebra, number theory seminar. So.
Cool, awesome. Are there any other questions for our speaker? All right, then I will stop the recording.
All right, thank you very much.